Hello everyone. Today we are going to talk about the first part of section 9.2, which is on the law of conservation of momentum. And our learning target today is to be able to mathematically support the law of conservation of momentum. So we're going to use our algebra skills to prove that this law is true. And our questions today we're going to try and answer: under what conditions is momentum conserved? How do we use the law of conservation of momentum to predict the behavior of objects? And how does Newton's third law relate to the conservation of momentum? All right, so let's start with some review. You know that's what I prefer to do. So last time we talked about the definition of momentum. So if you remember, momentum is the quality of motion. Every moving object has momentum. And the way that we calculate that is P. P stands for momentum. We don't know why, it just does, equals m times v. The impulse momentum theorem, which is what your Edpuzzle was on last night, so hopefully this sounds familiar to you as well. The impulse on an object is equal to the change in momentum. Right? So if you have an object that's moving around and you do something to it, you kick it or hit it or stop it or it runs into a wall, its momentum is going to change, and the impulse, the force that caused that to change, that's the impulse. All right, and our impulse momentum formula, I should change this. Impulse, sorry, I didn't notice that. The impulse momentum formula, Ft, that's impulse, is equal to m delta v, that's momentum. Remember that triangle is the letter delta, and it stands for the change in, so that means the velocity is changing, right? Mass is constant, mass won't change, but the velocity is speeding up or slowing down, changing direction, something's happening there. All right, so here's our new stuff, the law of conservation of momentum. Now keep all this review stuff in your head while we go forward, okay? The conservation of momentum. So this says momentum in a system. We'll talk about what a system is in just a minute, but that's an important word. Is constant before and after a collision. All right, so whatever the momentum of this system is before a collision, that's the same as the momentum after a collision. Now here are our conditions. Remember, that was one of our questions up above. What's a system? And a closed, isolated system. So these are the conditions under which momentum is conserved. It has to be a closed, isolated system. So what's a system? A system, a system is two or more interacting objects. Now we're going to stick with just two objects because otherwise the math gets really tricky, but it can be more than that, okay? A system is two or more interacting objects. A closed system is when mass doesn't change. And you're going to be like, but Mrs. Parent, you already told us the mass never changes. Right, but what I mean is the mass of the system doesn't change. So if my system is two bowling balls, the two bowling balls don't break in the middle of this thing, and so they get smaller. Or if it's two elephants, the elephants don't eat a lot of grass in the middle of the problem so that their mass changes, right? So the mass of the system is going to be constant. And an isolated system is one in which there's no outside forces. So what does that mean? Well, if there are no outside forces, then we're just worried about what happens when the two carts hit each other, and there's not going to be, somebody dropping a rock in the middle of our problem or something. So there's no outside forces. Okay, so spend a second. Make sure you've got those terms set up. We've got a system, and our system has to be closed and isolated. And in that case, momentum is conserved. Okay, so all of those ideas have to go together in your head. All right, how would I do this? How would I find the momentum of a system? So to find the momentum of the system, we calculate the momentum of each object and add them. Not too hard, huh? So if I have, my system here in a minute is going to be these two little glider carts. All right, and so I would take the momentum of glider cart that's red and the momentum of the glider cart that's blue, and I would figure those out, and I'd add them together, and that would be the momentum of my system. Right? It's really not very difficult. But you might be able to see now why we like to have just two things in our system, because otherwise the math just gets really bogged down. All right, so let's do this example and just see what we have here, okay? So in order to find the momentum, I need to know the mass and the velocity. So I'm going to change colors here. So we've got our calculation in a slightly different color. Okay, so the momentum of glider 1, I'm going to call that mass 1 times velocity 1. And the momentum of glider 2, we're going to call that mass 2 times velocity 2. And that's going to give me my total momentum. All right, so we need to come over here and take a look. I've got, this is going to be glider 1, and this is going to be glider 2. And I've got a mass of 1 kilogram, a velocity of 5 meters per second. So over here, I'm going to say mass is 1, velocity is 5. Okay, now we're going to do the same thing for glider number 2. I've got a mass of 1 and a velocity of negative 5. Okay, so I've got 1 times negative 5. All right, so 1 times 5 is 5. 1 times negative 5 is negative 5. Don't you like it when I pick the hard math problems for these examples? And remember, we label them kilogram meters per second. Okay, so 5 and negative 5 is 0. So the total momentum of my system is 0, because this momentum going this way is going to cancel out that momentum going that way. Remember, these are directional things, right? The vectors, the direction is important. Okay, so now these two gliders are going to collide with each other. They're moving toward each other. They're going to hit. And I want you to pause the recording. I want you to think about what could happen if these gliders collide. I'll give you an example of what I mean. So if the two gliders collide, one thing that could happen is they could bounce off each other. Oh, I can't spell could. They could bounce off each other. All right, so do a little brainstorming. Think about B and C. Turn the recording back on when you're ready to go on. Okay, I hope you came up with 2 other ideas. So what's really happening here is that these two gliders, are going to collide and stick together. So I've got glider 1 here, I've got glider 2 here, but because they have stuck together, they're really only one mass. So they are considered now one object. I hope that makes sense to you, right? Because now they're not going to move independently of each other. They're only going to move while they're stuck together. And this is called an inelastic collision. Now, if they bounce off each other, that's called an elastic collision, and that's something totally different. So this is an inelastic collision because they've stuck together. Okay, so now I want you to pause the recording again. I want you to compare the before picture and the after picture. So that's this one here, right? That's the before the collision. And this one here is the after the collision, okay? And I want you to write down at least one thing that's the same and at least one thing that's different, okay? And turn it back on when you're ready to go on. All right, what did you see? Did you see that their velocities are different? Did you see that their individual masses are the same, but the overall mass is different? Did you see that they're moving in the beginning and not moving in the end? Okay, those are some of the things that you might have seen. All right, so how do I calculate the momentum of the system after the gliders collide with each other? So I'm still going to have glider 1 and glider 2, but now they're stuck together. So instead of writing them separately, I'm going to say the mass of the 1 and the mass of 2 are, because they're stuck together, and they're only going to have one velocity, right? Because they have to move together, so there's only one velocity now. And that's going to give me my total momentum. Now, if our law of conservation of momentum is true, then whatever we got at the beginning is what we should get at the end. So if you think back, as a matter of fact, let's go back. So remember what we did here when we found the total momentum of the system. It was 0, right? Because the two momentums were in opposite directions and they canceled each other out. So if we've done this correctly now, we should end up with 0 here as well. All right, so let's plug some numbers in. The masses didn't change, so I've still got 1 kilogram for glider 1 and 1 kilogram for glider 2. And if I look up here, I can see that my velocity is 0. So I'm going to plug the 0 in. You saw this coming, didn't you? And so the total momentum is still 0 kilogram meters per second. Even though they're now stuck together, right? The momentum of my system before and after are the same. So what do we know about the momentum of each individual glider? Before the collision, well, glider 1, right, had 5 kilogram meters per second, and glider 2 had negative 5 kilogram meters per second. And after, they both had 0 kilogram meters per second, right? Because they weren't moving. So now, shut off the recording again. How does the momentum of each glider change after the collision? Okay, so you should have noticed that each glider went from having some momentum to having 0 momentum, right? The momentum of each one went to 0. But if we look at the system before and after the collision, before I had 0 kilogram meters per second as my momentum, and after I also had 0 kilogram meters per second as my momentum. And so, what does this momentum of the system, how does the momentum of the system change after the collision? All right, last time, turn it off. How does the momentum of the system change? Turn it back on when you're done. All right, hopefully you noticed that they were the same, right? It was 0 before and 0 after, even though the configuration of those gliders was different. All right, we're almost done. You guys are doing well. Here we go. Review, Newton's third law. This is good review for the final as well. Let's see, new section, new color. What do you want? Oh, I think green. Okay, so you remember what Newton's third law is? All forces, can you finish it? Come in pairs. What do we say about these pairs of forces? They are equal in size and opposite in direction. And if you think back, you can think about the force diagrams that we drew, right? The parallel force is equal and opposite to the friction force. The normal force is equal and opposite to the perpendicular force, right? Forces come in pairs. How does that fit into this momentum and impulse stuff? The force of glider 1 on glider 2 is equal to the force of glider 2 on glider 1. In other words, however hard they hit each other, if you're going one direction, it's the same hardness they hit each other going the other direction. And the car crash video that we watched the other day talked about that too, right? That the forces are equal and opposite. The size makes a difference, but the forces are equal and opposite. All right, couple more example problems here so that we can do our lab in class next time. So we have 2 laboratory carts, 1 kilogram each. So I've got the mass of, oh, not that one. The mass of cart 1 is 1 kilogram. The mass of cart 2 is also 1 kilogram. And then it says the cart on the left has a velocity of 5. To the right, the cart on the right has a velocity of 1. Also to the right, so everything is going to the right, so I don't have to make anything negative this time. So the velocity of cart 1 is 5 meters per second, and the velocity of cart 2 is 1 meter per second. And if you look, right, it tells you. So 1 kilogram, 5, and 1. Okay? All right. And then it says calculate the momentum of the system. All right, we know how to do that. So P1 plus P2 is going to give us the total momentum. And if I have M1V1 plus M2V2 gives me the total. So I'm going to have 1 times 5 plus 1 times 1. That's going to give me 6 kilogram meters per second, right? Check my math. I think I did that right. 5 times 1 is 1. 5. 1 times 1 is 1. Okay, 6. All right, so there's my answer. This system has a momentum of 6 kilogram meters per second. All right, it says after the carts collide, they stick together and move to the right, so still the positive direction, with a velocity of 3 meters per second. Find the momentum of the system after. Okay, so I have the mass of glider 1 is still 1. The mass of glider 2 is still 1. But they only have one velocity now because they're stuck together, and that's 3 meters per second. So I'm going to say the momentum of 1 plus the momentum of 2 gives me the total, but this time I know they're stuck together, so my formula looks a little bit different, right? And so I can say 1 plus 1 times 3 gives me 6 kilogram meters per second, which is exactly what it should give me. So that's wonderful. Isn't it nice when it works out the way you want it to? So can we combine these then? Can we, since these two formulas are equal to each other, can we just make them literally equal to each other? Of course we can. Let's see what that looks like. So if I write this out as one big formula, I get M1V1 plus M2V2 equals parentheses M1 plus M2V2, right? I have a before, that's the momentum of my system before, and here's the momentum of my system after, right? And those have to be equal to each other because law of conservation of momentum. So let's try using this big formula on this problem, shall we? 2 laboratory carts are on a frictionless surface. The cart on the left has a mass of 2 kilograms, so we'll call that one 1. 2 kilograms. An initial velocity of 7, so V1 is 7. To the right, okay, so it's positive. The cart on the right has a mass of 1, so this is cart 2. My mass is 1 kilogram. And it says it has an initial velocity of 1 meter per second to the right, so it's going to be positive, so that's good. So V2 is 1. The carts collide, stick together, and move off toward the right. Calculate the final velocity. So this is something different. We haven't had to do this before, but I think we can handle it. So what are we looking for? We are looking for the velocity after the collision, right? So if I say M1V1 plus M2V2 is equal to, parentheses, M1 plus M2V2. Maybe I should make that say after. Let's plug in what we know. 2 times 7 plus 1 times 1 is equal to 2 plus 1. And this is what we're trying to find. Okay, so let's do some math here. 14 plus 1 equals 3V. I got 15 equals 3V. Divide both sides by 3. And V, not N, V is equal to 5 meters per second. Okay, so now let's see. Does that make sense? So If this glider is going along at 7 meters per second and this glider is going along at 1 meter per second and they hit each other, does that mean that they're going to be sticking together and moving slower? Sure. So this is 7 meters per second. This is 1 meter per second. And this is 5 meters per second. Why are they moving slower? Because the mass got bigger, right? It's not 1 and 2 anymore. I mean, it's not 1 and 2 anymore. Now it's 3. So their overall momentum is the same, but the mass is smaller. Mass is bigger, my bad. So the velocity is smaller. Okay. As always, go back through here, highlight anything you want to ask me about during class time, and I'll see you next time. Thanks so much.